So today, as you can see up on the smart board, we have the ideal gas law. That we are going to be discussing. And with the ideal gas law, we have what we call the ideal gas equation. And this equation is really a combination of three simpler equations. So as we go through those, you will see that the first one is Boyle's law. And this stuff up here, okay, I'm going to help you understand that, what all this stuff means. Boyle's law. At a constant n and t. Okay? At a constant n and t. And what n is the number of moles. T is the temperature. So if the number of moles and the temperature are constant, then the volume of a gas is inversely proportional to the pressure. Now let's talk about inversely proportional. Have you ever dealt with that before? What that means is if one goes up, the other one goes down. It's inverse. As one goes up, the other one goes down. So stop and think about a balloon if I'm holding it. Okay? If I add more pressure, if I increase my pressure, what happens to my volume? What happens of the balloon? I increase the pressure on the balloon. Can I squeeze it together and make its volume smaller? Okay. If I decrease the pressure I put on that balloon, it will expand. So, at constant amount of moles and temperatures, the volume is indirectly proportional to the pressure. That is Boyle's law. The second one is Charles' law. Yes, that's Boyle's law, if we have the constants.
Is that like contribution characteristics getting an A or something?
What it is, it's a Greek alpha, okay? So it's a Greek letter, and it just shows a relationship, okay? You're going to see that we're going to eventually add a constant to that to turn it into an actual equation. So that little alpha right there that you see in both of those, that is just showing that there is a relationship. All right. Now, what Charles' law states is that if we have constant amount of moles, if our amount of moles is constant and our pressure is constant, then the volume is directly proportional to the temperature. So what would happen if I would increase the volume? The temperature would increase. What if the temperature decreased? What would happen to the volume? It would do what? It would decrease. Excellent. So that's a direct relationship. See how I've got the inverse right here, 1 over the P? When I just have the T there, it is directly. So volume is directly proportional to temperature if I have constant amount of moles and a constant pressure. Have you ever, let's say you've got a throwaway bottle of Mountain Dew that's almost half empty that you let sit in your car overnight and it gets really, really cold? When you come in there, isn't that smaller? Okay, can't you squeeze it more? Okay, try it sometime. You can do it with that bottle of water you have right there. Okay, drink most of the water, okay, and leave it sit in your car overnight and see what it looks like in the morning. Okay. The third law is Avogadro's law. Boy, we know that Avogadro, don't we? He's got his own number, man. Okay. Avogadro's got him his own number. Avogadro's law states that if we have a constant pressure and a constant temperature, then the volume is directly proportional to the moles. If we have more moles, doesn't it make sense that the volume's greater? If we have less moles, doesn't it make sense that the volume is less? Huh? Temperature. Okay? Temperature. So, I'm putting them all together, and I don't want this to confuse you, but what this is doing, and I don't even care if you write down these, okay? But all I've done is I've combined the three, and I've said that the volume is directly related to the moles and the temperature, and it's inversely related to the pressure. And when I do that, if I add this constant instead of the directly related, I can turn that into an equal. So what is the constant? R. R. So we call the letter R the gas constant. And by working my equation just slightly and taking this P out of the denominator, so I have everything in the numerator, I get this thing called PV equals nRT. PV equals nRT. Well, what does R equal? Okay, what does something mean if it's a constant? If something is a constant, what's it mean? It's always the same, right? Okay, so your value of R will be the same. So, let's look at this. We have conditions at standard temperature and pressure. We've already talked about STP. We stated that STP was 0 degrees Celsius, 1 atmosphere of pressure, correct? So, STP, temperature 0, pressure is 1 atmosphere. We know in an experiment that if I have 1 mole of a gas at STP, it's 22.4 liters, correct? That's a molar conversion. 1 mole equals 22.4 liters. Therefore, if I have PV equals nRT, could you solve for R? Do you have the ability to solve for R on that equation? What do you think? Sean's nodding his head, says he can do it. What would R be equal to? PV over NT, right? We just manipulate our equation. So R is equal to PV over NT. Well, what's our pressure? We're at STP. What's our pressure? Yeah. You're going to see that the label of this is going to be funky. Okay. What's our pressure up there? 1 atmosphere, right? What's our volume? 22.414 liters. What's our moles? 1 mole. What's our temperature? 0. So if we would do those, 1 atmosphere, 22.414 liters, multiply those together and divide by the temperature. Look what I did to the temperature. What did I do? I changed it to kelvins. What's the advantage of having kelvins? What's the advantage of having kelvins over degrees Celsius? What's the advantage? What's the difference? What do Kelvin not have? Okay. Kelvin, you could get absolute 0 as 0 Kelvin. Okay. So you could hit 0 Kelvin. But one thing that Kelvin does not have is negative numbers. Okay. Kelvin does not have negative numbers. So we have to convert that temperature into Kelvin. When I do so, and I do that math, I get a value of R to equal 0.082057. I've taught you how to convert to Kelvin. Celsius plus 273.15. Oh, we haven't gone over a Kelvin? Okay. Kelvin. I thought we have. All we have to convert from Kelvin, put this as a side note in your notes, degrees Celsius plus 273.15. So a common one that we see is 25 degrees Celsius. If I have 25 degrees Celsius, how much Kelvin is that? $298.15. Okay, it's not a tough conversion. I just thought we've already done it. We haven't even talked about Kelvin. All right. 273.15. That's my bad. I thought we've talked about Kelvin before. Now, let's look at this label, okay? Let's look at this label. We have an atmosphere times a liter, right? All over a mole times a Kelvin. So, that's exactly how I'm going to label it. And you can see that I just flopped those. I probably should have had atmospheres first, liters second to be consistent with what I had up top, but it doesn't matter. They're both in the numerator, and moles times Kelvin is in the denominator. So that's a funny label, isn't it? Well, what that allows us to do is when we start looking and canceling labels out, that allows us to get the correct label when we start working these problems. So I'm going to give you a second here. Go ahead and copy down everything with this problem here, and then we'll talk about it after you get it copied down. All right. If I'm looking at this, okay, I have a balanced chemical equation right here. Would you agree? Okay, I have a balanced chemical equation here. Now, this is a gas law problem, so you can assume, you can assume that you're going to be using PV equals nRT. So in order to do these problems, I have to have 4 out of the 5 variables, right? Now, let's check this out. I'm always going to have R because it's a constant, right? I just have to match up my labels, okay? What else do I have here given to me? I have a T. My T is in Celsius, though, so I have to convert it to Kelvin. Okay? What else do I have given? What else do I have given to me? Pressure. If I read the problem, what is it asking me to find? Volume. So somehow, I've got to come up with N. And what did I tell you N was? Number of moles, right? Well, here's the beauty of this, folks. Okay? Here's the beauty of this. I want to find the volume of chlorine gas, right? Could I find the number of moles of chlorine gas with the information that I have given to me? Yes, I can, right? How am I going to do it? How am I going to do it? I have to convert 13 grams of aluminum chloride to moles of chlorine gas. Okay? So what I want you to do is I want you to do that right now in your notes, and then I'm going to do it up here on the board. So make that conversion right now. You should know how to do that. Okay, I see some people talking about this. Let's go ahead and let's just work it. I have 13 grams AlCl3. I am going to convert that into moles. As I do so, I know that 1 mole AlCl3 is 133.340538 grams AlCl3. Where did I get that number? What is that number? It's the molar mass of aluminum chloride. So, I get my grams to cancel. I've now converted this into what? Moles of aluminum chloride. Now I need to use my molar ratio to get to moles of chlorine. So I see that 3 moles of chlorine is 2 moles AlCl3. That is my molar ratio, correct? So when I do my math, and I take 13, divide it by the molar mass, and then I come up with a value of 0.14624. I'm taking it out as many as possible because I'm not done yet, am I? I'm not done yet. Why am I not done? Because I've got to plug that back into PV equals nRT, right? What did I just calculate there? Moles of chlorine gas, which is what in my PV equals nRT? N. Okay? Now, all I simply need to do is, and I'm going to erase this, okay? Keep that number right there. I'm going to erase my molar conversion here. Now what I need to do is I need to substitute in to PV equals nRT. What is P? 1.15 ATM. What is V? I don't know V. What is N? 0.14624. What's my label? Moles. Now, what is R? What is R? What did we call R? A constant, right? And that constant was 0.08205.7, and let me see if I remember, liters times atmospheres over mole times Kelvin, right? It's the constant we just calculated in your notes. Constant, yes. Now, I don't want to confuse you, but the only way that ever changes is if you use something different over here. For instance, do I have to use a pressure in atmospheres? Okay. Most commonly here, like if we take our barometric pressure outside, it's in millimeters of mercury. It's not in atmospheres. So the pressure could change. Okay? But I'm not going to do that to you yet. What's the final thing I need here? T, which is temperature, 298.15 Kelvin. I converted it. So how am I going to solve for volume? I'm going to divide 1.15 ATM. So I get a cancel there. 1.15 ATM. So when I do that math, I take my number of moles, I multiply that by my constant, my temperature, and then I divide that number by 1.15 atmospheres, and I get a value of V equals 3.11117. Is that what you got when you divide it out? Now, I need to go back. I need labels. Okay? I need labels, and I need to do sig figs. How many sig figs should I have here? 2 right here, 2 right here, 3 right there. What's my lowest amount? 2. I'm going to have 2 sig figs. So my 2 sig figs is going to be 3.1. Now when I look at this, here I have a mole and a mole on the bottom, top bottom. Here's a Kelvin on top, here's a Kelvin on bottom. Here's an atmosphere on top, here's an atmosphere on volume. What do I have left? An L. Is that a label for volume? Absolutely. So, voila. There I go. I have done my first gas law problem. Now, was that a long one? Yeah. Was it anything that is impossible? Absolutely not. Okay? Absolutely not. It's very possible. Okay?
Are you gonna have to memorize like the constant?
Like the value for the constant? I don't think it's tough. 0.0821 is usually what we call it. 0.0821. Now, we've got about 10 minutes left. So let's look at one more of these, and then we'll save the rest for later. So go ahead and write this example out, and we will calculate it here in 1 second. Okay, my problem says that if I have 2 moles of sodium and I react that with sulfuric acid, I form sodium sulfate with hydrogen gas being released. The question states, if 3.5 grams of sodium react, what pressure of hydrogen gas will result in a 250 milliliter container at 35 degrees Celsius? So once again, I have PV equals nRT. Once again, looking at the equation, okay, I have to calculate pressure. So pressure is my unknown. Do I have a volume? Do I have a volume? Yes, I do, but what do you notice about the volume? It's in milliliters. Can I use that value, or do I need to convert it? I have to convert that to liters. So how many liters is that? What's my conversion, milliliters to liters? 3 jumps what way? 3 to the left, so it's 0.250 liters. Do I have N? Nope. Do I have R? I always have R, don't I? Do I have T? Yes. Can I find N? Yes. So that's what we need to do first. We need to find N. What is N? We need the moles of hydrogen gas. So I'm going to convert 3.5 grams of sodium to moles of hydrogen gas. Once again, this is just stoichiometry that we have already done. So I know that 1 mole of sodium is 22.98977 grams of sodium, straight off of the periodic table. I know that 2 moles of sodium react to produce 1 mole of hydrogen gas. Let me go through and make sure my labels cancel. I have grams of sodium, grams of sodium. I have moles of sodium, I have moles of sodium. Leaves me with the value in mole of hydrogen gas. So, as I do my math, I get a value of 0.07612. Once again, I'm going to carry it out more than I normally would, because now I'm going to throw it back into my PV equals nRT. So, as I do so, pressure, I do not know. Volume is 0.250 liters. My number of moles I just calculated, 0.07612 mole hydrogen gas. My constant, let's see, that was liters, atmosphere, mole, Kelvin. And to convert that into Kelvin, that's going to give me 308. 308.15 Kelvin, right? To solve for P, I'm going to divide both sides by 0.250. So I get a value of 7.703156. I need to get a label. I need to get sig figs. I can see that I have 2 significant figures, right? So when I take that to 2 sig figs, it's 7.7. What's my label going to be? Here's a mole, cancel with the mole, right? Here's a liter, cancel with the liter. Here's a Kelvin, cancel with Kelvin. I'm left with ATM. So my pressure in this situation is 7.7 atmospheres of pressure. We will work more of these problems later on in the week. I think that there is a WebAssign that went active. So if you want to try some of these, a WebAssign went active today. It's not due until the 12th. So if you want to wait, you can wait until you know it a little better. But if you think you got it, you might want to try some of these.